Welcome to this tutorial on half-wave rectifiers. In this video, we'll explore the fundamental concepts of a half-wave rectifier, how it works, and why it's important in electronics. Let's get started. First, let's talk about what a rectifier is. A rectifier is an electronic device that converts alternating current, AC, which periodically reverses direction, into direct current, DC, which flows in only one direction. This conversion is crucial for many electronic devices that require a steady and unidirectional flow of current to operate properly. Now, let's dive into the components used in a half-wave rectifier circuit. In the image you see here, we have three main components: an AC voltage source, a diode, and a resistor. 1. AC voltage source. The AC voltage source is the input of our circuit. It provides an alternating voltage, which varies sinusoidally with time. In this example, our AC source has a frequency of 40 Hz and a peak voltage of 5 volts. The frequency of 40 Hz means that the voltage completes 40 cycles in 1 second, switching between positive and negative values. 2. Diode. The diode is a semiconductor device that allows current to flow in only one direction, from the anode to the cathode. In our circuit diagram, you can see the diode placed in series with the AC source and the resistor. The diode is the key component that enables the rectification process. When the anode is positive with respect to the cathode, the diode is forward biased and conducts current. Conversely, when the anode is negative relative to the cathode, the diode is reverse biased and blocks current. 3. Resistor. The resistor, marked as 640 ohms in our circuit, represents the load across which we measure the output voltage. The resistor's role is to limit the current and provide a measurable voltage drop when current flows through the circuit. Let's move on to the operation of the half-wave rectifier. We'll examine what happens during the positive and negative half cycles of the AC input voltage. Positive half cycle. During the positive half cycle of the AC input, the voltage at the anode of the diode is positive relative to the cathode. This forward biases the diode, allowing it to conduct current. As current flows through the diode, it also flows through the resistor, creating a voltage drop across it. The output voltage across the resistor mirrors the positive half of the input AC voltage. In this phase, the circuit effectively passes the positive portion of the AC waveform to the output. Negative half cycle. During the negative half cycle of the AC input, the voltage at the anode of the diode becomes negative relative to the cathode. This reverse biases the diode, causing it to block the current. Since no current flows through the circuit, the output voltage across the resistor drops to 0. As a result, the output waveform has no negative component. Next, let's take a closer look at the waveforms. On the left side of the image, we see the input AC waveform, which oscillates between positive and negative values, reaching a maximum of 5 volts. On the right side, we see the output waveform. Notice how the output waveform only shows the positive half cycles of the input AC voltage. The negative half cycles are completely eliminated, resulting in a pulsating DC output. It's important to note that the peak value of the output voltage is slightly less than the peak value of the input voltage. This is due to the forward voltage drop across the diode, which is typically around 0.7 volts for silicon diodes. Hence, the peak output voltage in our example is approximately 4.451 volts. Let's discuss some practical considerations of using a half-wave rectifier. One significant factor is the presence of ripple in the output voltage. The output is not a smooth DC voltage but a pulsating one with the same frequency as the input AC signal, in this case, 40 Hz. This ripple can be reduced using filtering techniques, such as adding a capacitor across the load resistor. Half-wave rectifiers are relatively simple and inexpensive to design but are less efficient than full-wave rectifiers, which use more diodes to rectify both halves of the AC input. Despite this, half-wave rectifiers are still used in various applications. Applications of half-wave rectifiers. Simple DC power supplies. Half-wave rectifiers are commonly used in simple DC power supplies for low-power devices. They provide a basic method of converting AC to DC for small electronics. Signal demodulation. In communication systems, half-wave rectifiers are used for signal demodulation, extracting information from modulated carrier waves. In summary, a half-wave rectifier is a fundamental electronic circuit that converts AC to DC using a single diode. It allows current to pass during the positive half cycles of the AC input and blocks current during the negative half cycles, producing a pulsating DC output. While not as efficient as full-wave rectifiers, half-wave rectifiers play a crucial role in many electronic applications. Thank you for watching this tutorial. We hope you now have a clear understanding of how half-wave rectifiers work. If you have any questions or would like to learn more about rectifiers and other electronic circuits, please leave a comment below or explore our other videos. Don't forget to like, share, and subscribe for more educational content.